Continuing with the different type of testing techniques, we are having next testing techniques as robustness testing. It is nothing but the expansion of boundary value analysis, where but the extreme values are exceeded with a value slightly greater than the maximum and a value slightly less than the minimum. That means we are having some local minima extended as well as local maxima extended. It means we want to go outside the boundary of input domain. This extended form of boundary value analysis is called robustness testing. There are four additional test cases as compared to boundary value analysis in robustness testing. So it will give 6n plus 1 test cases where n is the number of input variables. So now we will have 13 test cases as compared to boundary value analysis where we are having 9 test cases. So now comparing with this, we are having next for the boundary value analysis, we are having only the test cases at the boundary. Now one more test cases at every side has been extended. So we will have four more test cases. Now we are having test cases as 299, that is 200, and this for 99, 200 100, 200 101, 200 and 200, that is in the middle part. Now next is 200 and 299, this one, 200 and 300, 200 and 301. Same way at the left side we are having 99 and 200, 100 and 200, same way 100 and 201. Now next right side we are having 299 as well as 200, 300 and 200 and 300 with 201. Now next type of testing we are having worst case testing. So now extending the part of robustness testing, we are having worst case testing. So if we reject single fault assumption, theory of reliability, and we would like to see that what happens when more than one variable has an extreme value. That means we are checking the testing for every phase. In electronic circuit analysis, this is called worst case analysis. It is more thorough in the sense that boundary value test cases are a proper subset of worst case test cases. Obviously, we are having test cases for the variables for all boundaries. So that's why it is called worst case testing. It requires more effort. Worst case testing for a function of n variables will generate 5 raised to power n test cases as compared to boundary value analysis where we are having 4n plus 1 test cases, while in the case of robustness testing we were having 6n plus 1 test cases. So while in the case of worst case testing, as we are having variables testing for all type of values, so that's why it is 5 raised to power n test cases as opposed to 4n plus 1 test case for the boundary value analysis and 6n plus 1 test case for the robustness testing. So for the two variable example, we are having 5 square, that means 25 test cases as given in the next table. So these are our worst case testing that are checking the values for x and y for all possible scenarios. So we are having 25 test cases in total. So next, consider the example of determination of nature of roots of a quadratic equation. The same example we have taken in boundary value analysis. Now robustness test cases will be 6n plus 1. That means we are having 19 test cases. So it will be like this. We are having A, B and C. We have extended one more value at the left, right, bottom and top side as compared to boundary value analysis. So we will have right now 19 test cases. So as compared, if we will compare it as compared to boundary value analysis, we are having more test cases. So same way, if we will evolve worst case testing, we will have 5 raised to power n, that is 125 test cases. Now we are checking for every value of the variables. This one, this, and next is this one. 82 test cases, 100 test cases, 118 test cases, and last is 125 test. For more test cases, testing is called equivalence class testing. Name suggesting this is the equivalence class. That means we are partitioning the program into a finite number of equivalence classes such that we can reasonably assume but not be sure that the test of a representative value of each class is equivalent to a test of any other value. So we are having two steps required for the implementing this method. The equivalence class are identified by taking each input condition and partitioning it into valid and invalid class. So we have partitioned the problem into valid and invalid class problem. Next is generate the test cases using the equivalent classes identified in the previous step. This is performed by writing test cases covering all the valid equivalence class. Then a test case is written for each invalid equivalence class. That means we are writing test cases for valid as well as invalid equivalence class. So for this diagram, we are showing input domain, after that system under test, and now we are having output domain. That means we have divided the problem into valid as well as invalid partition. So most of the time, equivalence class partition class testing define classes of input domain. Our equivalence classes should also be defined for output domain. We should design equivalence classes based on input and output